So in the previous lecture we had discussed examples, definitions, and a few elementary concepts related to metric spaces. In this particular lecture we will be mainly focusing on concepts like balls, spheres, and we will be kind of trying to introduce the concept of open sets in this lecture only. If not possible, we will move on to the next lecture. Never mind. Uh, so basically, before moving on to balls and spheres, let us first discuss a few concepts more about restriction matrices. So restriction matrix is kind of, suppose you have a metric space XD. Okay. XD is a metric space. XD is a metric space, and you take a non-empty subset of X. You take a non-empty subset of X. Okay. Now see this D. This D is a function from X cross X to R. So in any way, if you restrict this metric to the domain Y cross Y, then you get a new metric. Okay. So if you restrict this metric such that its domain is restricted to Y cross Y, we note this metric as dy. Then this is a new metric, and Y with respect to dy forms a metric space. Okay. So subsets of non-empty subsets of metric space with respect to some restriction metric forms a metric space. This type of metric is called a restriction metric. Okay. Also sometimes called the restriction induced metric. Okay. D restricted to Y cross Y is also some term related to this. Okay. D restricted, this D restricted to Y cross Y. Okay. Better we write it as a restriction metric induced by D. Okay. One more such concept is that suppose you have two distinct metric spaces. For generalization, we take two distinct metric spaces. So suppose you have x1 d1 and you have x2 d2, two metric spaces. Now using these two metric spaces, you form a new set, let's say x, which is x1 cross x2, and you try to declare a function d with x such that d of xy is equals to d of x1 y1 plus d of x2 y2. Okay. Sorry, d1 of x1 y1, d2 of x2 y2. Okay. So this x1 y1, this is an element of x1 obviously, because d1 is the metric related to x1. x2 y2 is d2. Clear? And this x and y, these are elements of x. Okay. And since x is the cross product x1 cross x2, so basically x is of the form x1 x2, y is of the form y1 y2. Very simple to understand. Okay. Now you can obviously check that this is a new metric. This is a new metric, which says that we have induced one more metric using these two metrics to form a new metric space. Right? You can also choose one more such induced metric. For example, let's say you have d of xy as the maximum of d1 of x1 y1, d2 of x2. This will also form a new metric. Okay. These two are very, very trivial to check. You can do it on your own. Okay. Now let us move on to the main focus of today's lecture, which is the concept of open balls, closed balls, and spheres. Okay. So let us give the heading. So open balls, closed balls, and spheres. Open balls, closed balls, and spheres. Okay. So let us have a metric space XD. So let XD be a metric space. Okay. Okay. Now we choose an element from this metric space. Let's say A. Okay. Let A be an element of X, and let R be a positive real number. Let R be a positive real number. So using these two, we define what we call an open ball as UAR, which is the which is the set of all those elements of X such that the distance between A and X is always less than R. Okay, this is what we call an open ball. Okay, now there might be some shape coming to your mind. Okay, you can use that imagination to understand this concept, but don't just gradually fix this imagination in your mind, because shapes of these open balls, closed balls and spheres vary according to metric spaces. Okay, they vary according to metric spaces. In some fixed metric space you will have the same shape which is coming to your mind, but that will not always be valid. Okay, so don't just fix that shape, but you can use that shape to imagine the concept, or for a better understanding of this concept. Okay, so this is the concept of an open ball. Okay, this R is called the radius of the ball. This R is called the radius of the ball. Radius of the ball. Okay, similarly we define what we call a closed ball as BAR, which is given as X belongs to capital X such that distance of A and X is less than equals to R. Okay, so basically you can think it like this, that UAR is simply the region. UAR, that is the open ball, is simply the region which obeys this condition. Okay, while BAR is the region as well as the boundary, the region as well as the boundary which obeys this condition. Okay, basically if you talk about the sphere, it will be a more a clearer understanding. Suppose you have a sphere. A sphere is defined as the as all elements of X such that distance of A and X, okay, this is X not R, A and X is equals to R. Okay, so now this is pretty much clear to understand that this open ball along with this sphere gives you the closed ball. Okay, this open ball along with this sphere, it gives you the closed ball. Okay, acha, to support your imagination, let us first take an example of this concept, and then we will be understanding the other things. Okay, let us first take the example of this concept. Okay, see, very simple to understand. See, suppose we talk about in the R2 metric space. Okay, with the Euclidean domain, let's say. So the first example we are talking about is the R2 metric space with the Euclidean domain. Okay, Euclidean metric. Okay, so you remember D2, right? D2 of xy equals to summation yi minus xi, its mod squared whole 2, right? Okay, now let us say you take r as 1, a as 0. Okay, you take r as 1 and a as 0. Okay, and you take an element from R2 such that x is written as x1 x2. Clear? So now if you try to define the open ball, okay, so UAR is the set of all those such elements. Okay, this is basically a general representation of the element of R2, which I was trying to say. So these this refer to all those elements of X such that here X is R2, right? Here X is R2, so let me write R2 only. Okay, R2 such that distance between, we have taken the Euclidean metric, so distance between A and X is less than R or less than 1. Now see, A is 0 means basically this is in the form of coordinate because A is an element of R2 itself. So how can we write this? So this is the set of all those elements of R2 such that the d of x can be written as x1 minus 0 squared plus x2 minus 0 squared whole root less than 1. But this is basically the region. This is basically the region denoted by a circle whose radius is 1. The region inside a circle whose radius is 1. The region inside a circle whose radius is 1 and center is origin. So next page, if we draw the shape, so it's very simple to understand. So this is the center of the circle, and let's say this is 1 0, this is minus 1 0, this is 0 1, and this is 0 minus 1. So okay, so this is the region. Okay, this is the region. This 0 1 0 1 1 0 minus 1 0 and 0 minus 1, and this whole boundary is not at all contained in the region, in the open ball. Okay, in the open ball. Clear? The region inside it, let me try to draw it. So this region inside it, this region is what constituting the open ball. Okay, is it clear? Now similarly, in the same way, if you draw the closed ball, I need not write it again. So this will basically imply the region given by x1 square plus x2 square less than equals to 1. That is this circle as well as the region inside it. The closed disk, you may say, a disk including its boundaries. Okay, so this is the disk of radius 1 with its boundary. What is the boundary? The boundary is the unit circle basically, which is the sphere. Okay. If you draw this sphere, you can now see, when you have understood the concepts of the open ball, you can do it for the closed ball and sphere on your own, right? So what is this sphere? The sphere is basically this open circle, right? It is basically this open circle. Very simple, right? Okay. So this open ball along with the sphere gives you the closed ball. I hope people have understood it. Okay. Now a few terminologies related to this concept of open ball and closed ball. If you study Siemens book, I do not know the exact spelling of the book. Okay, you will be uh, getting the terms like open spheres and closed spheres. Okay, open balls will be their open spheres, and closed balls will be closed spheres. Okay, don't get confused. Whatever terminology you have set up in your mind, just follow that. In Rudin's book, you will get the concept of open ball as the neighborhood of it, open neighborhood of it. Okay. And in some books you will be getting the terms like open and closed discs. Okay. So whatever terminology you feel like, you just follow that. That's not a problem. Okay, now let us discuss the basic example, which is the concept related to discrete metric space. Okay, so let XD be a discrete metric space. Okay. Oh, 1 second, guys. 1 second. 1 second. Okay, so sorry guys for making you wait. Okay. Just skip that. So let XD be a discrete metric space. So we already know what a discrete metric space is, right? So a discrete metric space is d of xy is 0 if x equals to y, and it's 1 if x is not equals to y. Okay. Now let us say we take a equals to 1, and let's say r is equals to 1 itself, let's say. Oh, let's take a equals to 0 and r equals to 1. That might be better. Or let us do one thing. Let us take a as an arbitrary element. Let us not fix a. So a is arbitrary. We are fixing this radius. Radius. Let's say r is 1. So what is ua1? Let's say. So it is the set of all those elements from this discrete metric space such that distance between a and x is less than 1. Now see, the distance between a and x can either be 0 or be 1. So if it is less than 1, then it can only be 0. And when is this possible? If a is equals to x. So the set of this element, so the elements in this open ball is basically the singleton set. Okay. So this was the first example which did not follow your imagining shapes, right? So this is a singleton set. This is a singleton set, right? Okay. So if you choose the closed ball, let's say, okay. Now see, every element from the metric space will have its distance from A either 1 or less than 1, which is 0, right? So the closed ball will give you the whole of the metric space. Very simple, right? It will give you the whole of the metric space. Clear? Also, suppose you take a closed ball, where your r is less than 1. So the only possible case, the distance between x and a is less than equals to 1, right? Less than equals to not 1, where r is less than 1, right? So the only possible case can be 0. The only possible case can be 0. So it will again be the singleton set. Suppose you take a sphere A, radius is 1/3, let's say. Will there be any such element whose distance from A is 1/3? No, because every element has its distance from A either 1 or 0. So it will be an empty set. Clear? Clear? Suppose you take the sphere A1. Okay. Now this is C. So for all elements, set of all elements of x such that distance of A and x is 1. Okay. So every element from the metric space has its distance from A1 unless it's equal to A. So this is the whole of the metric space except. So these were a few examples related to the discrete metric spaces. Clear? Now if we move on to uh, the real line, okay, with its usual metric, okay, D1, usual metric. So in this case, suppose you take UAR, okay, generalized concept. Okay, R is any positive real number and A is any element from R. Okay, so this is the set of all those elements from the real numbers such that distance of A and X is less than R. Right now, this usual metric is basically the norm, right? So it will give you basically the form of this. So x minus a, you might say x minus a is less than r. Okay, x minus a is less than r. Achha, can you write it as this region a minus r to a plus r interval, this open interval? Intervals you people have already studied, right, in real numbers, real analysis. So this open interval will give you the open ball. Okay, this open interval will give you the open ball. In a similar way, if you try to find the closed ball, this will be this closed interval because you only have an additional equality here. Okay, if you talk about the sphere, so what will the spheres be? So I have already said that spheres basically seem to be the boundary of this open ball. So what is the boundary of this open ball? A minus r and a plus r. So this is the set of only these two elements, a minus r and plus r. Clear? You can check it on using the definition. Okay. So what I'm trying to portray here is that this terminology, balls and spheres, they do not resemble the shape. Okay. But just it just projects an idea in your mind about the concept, right? Clear? Okay. Now next there is a very important theorem related to balls and spheres and real analysis. Okay. This is very important. See, what are the intervals which we are already acquainted with? So we have studied, I think 9 intervals. Okay, so I'm writing them down. So we have this interval, closed interval AB, open interval AB, okay, left closed interval AB, right closed interval AB. Then we have studied the left closed ray, left open ray, uh, right open ray and right closed ray, and the real line, right? So you have, yeah, nine intervals, right? In these 9 intervals we have studied. Okay. Now, now we will be studying a very important definition of intervals, which is not which we have already studied in the concept of real analysis. This is a more generalized version of what intervals actually mean. Okay. See, real analysis or real line is basically a special case of studying metric spaces. Okay, it is a special, it is one of the kind of metric spaces which we have already studied in details in real analysis. That's a real number is a metric space, and everything you have studied in real analysis is basically defined on the basis of its usual metric. Okay, so defining terms in the metric spaces basically is followed in the real analysis, right? Here, in case of metric spaces, we studied in a more generalized manner. Okay, so what is the actual definition of metric space of intervals? Is that suppose you take a set from R. Okay, see, intervals in this case basically rely on the real line itself, but the definition actually comes out like this: that let there be a non-empty set from R. Okay, then I is said to be an interval if for all xy belonging to I, let's say where x is less than y, every element between x and y also belong to it. Okay, let me write it in the statement form. Okay. Every element between x and y is also in I. Okay, so this is the definition of an interval, and from this definition there comes out a theorem. Which is very important. The theorem is like, let let us take a non-empty subset of R. Okay, prove that I is an interval. I is an interval if and only if I is one of the above 9 types. Okay, so if I is one of these above 9 types, it's an interval. And since there is a biconditional statement, so any of these 9 types is an interval, and if such, so basically these 9 types of intervals are only the existing intervals. These 9 types of intervals are only the existing 9 types of intervals. If you take a set which resembles any of these sets, so it's an interval, and if any of these sets you consider, then it's an interval. Okay, sounds confusing. Now see, proving that I is one of these 9 sets, hence I is an interval, it is very trivial because these 9 are already intervals. We have already studied them as intervals, right? So that is a trivial case. What I try to say is that proof, see, what I try to say is that if I is of the above 9 types. Okay, it's an interval because these 9 types were already interval. We have discussed them as examples of intervals, right? It's an interval, which is trivial, right? Which is trivial. Hence, no need to prove. Hence, no need to prove. So we prove the other way around, that if I is an interval, then it is one of the above 9 types. Okay, let us prove that. So let us take that as a converse. Okay, so we choose I to be an interval. So let a non-empty subset of R be an interval. Okay, be an interval. Now, why we are taking a non-empty subset? Because if it was empty, then that in that case also it is trivial. Okay, if I is empty, then in that case also it is trivial. Right. That is not even a topic of consideration. Yeah. So we assume it to be an interval. Now what we do is that we divide this into two cases. Okay. In one case we choose that I is bounded both below and above, and then we choose I is bounded only above or only below. Okay. Okay. So we what we do is, suppose we take case one. Okay. In under case one we have I is I is bounded both below and above, both below and above. Okay. Now using the LUB axiom of R, we can always say that since this is bounded below and it is bounded above, so there exists its least upper bound and greatest lower bound. Okay. Right. Okay. So by the LUB axiom, we can say, okay. So using the LUB axiom, we can say it has its LUB and its GLB, or infimum or supremum. Okay. So let A be the infimum of I and B be the supremum of I, or the LUB of I and the GLB of I. Now let us choose an element from between A and B. Okay, so let X belong to AB, or let us write it like this, that A less than X less than B. Let A less than X less than B. Okay. Achha, now since X is greater than A, implies X is not a lower bound. X is not a lower bound, right? Lower bound of I, obviously, which implies there exists some C in I such that A is, it lies between X and A. Okay, it lies between X and A. Okay. Similarly, since X is less than B, implies X is not an upper bound. X is not an upper bound. Hence, there exists some D in I such that X is less than D less than, so D lies between A and B. Okay, now see, A is the infimum of I and B is the supremum of I. Right? A is the infimum of I and B is the supremum of I. Right? Now what we do from here is that, see, so this D belongs to I, this D belongs to I, and this C also belongs to I. Okay? So what we have proved is that, so this basically implies that there exists C and D belonging to I such that, so the X is contained in C and D, such that X is contained in C and D. Is it clear? Is it clear? Now see, I was chosen to be an interval. Since I is an interval, since I is an interval, so C and D is contained in I, so every element between C and D will also be contained in I. Since I is an interval, X must be contained in I, right? X must be contained in I. Now, X is an arbitrary element. X is an arbitrary element of let's say this open interval AB, which we already know. So X is an arbitrary element of AB. This means that AB is contained in I. This means that AB is contained in I. Is it clear? This follows that AB is contained in I. Now what we can do is that if we follow the same steps, repeating the same steps using some y such that A is less than equals to y less than equals to b, we can show I is contained in closed interval AB. I is contained in closed interval AB. And using these two facts, so what we basically got? So we basically got this open interval AB is contained in I, which is indeed contained in AB. So this I is either of the form AB or of the form open interval AB or of the form closed interval AB, provided the interval is bounded from both below and above. Now what we can do is that now we can choose the same steps taking equality on one side. Okay, we can choose the similarly choosing some z such that a less than z less than equals to b. Okay, this will provide you with the concept that I is of the form left open right closed. If you take the equality on the left side, right, you will get the left closed right open. Give you the notion that I is either of the forms open interval AB, closed interval AB, left closed, right closed. Okay, so this was about case 1. This was what we needed to prove. The same thing you can do for case 2, taking it only bounded above or below. Okay, in case 2 what we do is that let I be bounded above. Let I be bounded above. Okay, now I am proving this for bounded above only, and you can do it on your own for bounded below. The same steps you need to follow. Now see, if it is bounded above, we can do the same thing. Okay, so let you have B as the supremum of I. So now let there exists some x which is less than b, let's say. Okay, which implies the x is not an upper bound, of I, which implies there exists some d belongs to I such that x is less than d. Since I is an interval, x must belongs to I, which means that, so ranging from minus infinity to b, this is contained in I. Similarly, for some y which is less than equals to b, we get I is contained in left closed. So it is either of the form this or of the form this. If you choose I to be bounded below, then you can show that. Similarly, if I was bounded below, then I would have been of the form a to infinity or a closed, a closed to infinity. Okay, so it is either of the form this, and if it is neither bounded above nor bounded below, then that is trivial to be minus infinity to infinity. That's the real. Okay, so hence I being an interval, it is one of the 9 types discussed. Okay, so is it clear? Is it clear? Okay, let us discuss some more things about intervals. Let's say, will the union of two intervals be an interval? Is union of intervals interval? Oh, obviously not. So suppose you take 0 1 union 2 3. It is not an interval because elements between 1 and 2 are not there. Not an interval. Okay. When can it be an interval? 0 1 union half 3. It is an interval. Why? You can obviously check it, right? Because this half, this lies in this interval itself. So elements from half to 1 is also contained here. So this becomes a continuous form, right? So basically I1 union I2 at the individual intervals is an interval. If and only if I1 intersection I2 is not empty. Okay, and you can generalize this for in such uh, intervals. Okay, familiar. Clear? Clear? Okay. Now let us take. Try this on your own. Figure out the metric space. Figure out the metric space in which balls and spheres resemble their actual shape. Let us take this as an exercise. Okay. Now suppose we take this metric R2 and D1. Okay, R2 and D1. Okay. So what is D1 xy? So it is basically mod of y1 minus x1 plus mod of y2 minus x2. Where? So this is, so what is x of the form? x1 x2. Very simple. X is of the form x1 x2. And y is of the form y1. Right? Suppose you take the center as the origin and you take the radius as 1. So what is the open ball? So it is the region. So is that mod of x1 plus mod of x2 is less than 1. What is the closed ball? The closed ball is the same region with equality. And U, B and sphere. What the sphere will be? The sphere will be only the condition of equality. Right. Can you draw this shape? Let us try to figure out this shape. Okay. So let this be the real line. Okay. Now see, what are the extreme points? Okay. This is pretty much obvious to see that the extreme points here are the 0 1 1 0 minus 1 0 and 0 minus 1, right? So 1 0 0 1 minus 1 0 and 0 minus 1. Okay, and what are these modes, the equation of these particular lines? So it is pretty much trivial. You people have studied these sorts of graphs in your +2 level. Okay, so it is a very bad trick. I can't draw shapes here, that is the main problem. Yeah, so this line, yeah, here this line, this line, and this line. Yeah. Okay, these are straight lines. You don't go over my drawing. Is it clear? This region inside, this region inside, it is the open ball. Okay, this region along with its boundary is the closed ball, and this boundary itself is the sphere, right? Clear? Then now suppose we talk about functions. Let's say suppose we talk about functions. Okay, suppose we talk about functions. Suppose we take, say, let's C01. We take C01 along with, say, the soup norm. Okay, next example, we take C01 along with soup norm. Okay, what was the soup norm? It was the supremum of the difference between these between any two arbitrary functions taken from this particular set. What was C01? C01 was the set of all continuous real valued functions in the domain 01. Okay, clear? So I'm writing it down here. So the metric induced by soup norm Fg, it is basically the supremum the functions fx minus gx, majorly take its modulus. Okay, where x belongs to 0, right? Let us fix an index arbitrary. We don't read it further. We have not indexed anything. Clear? Okay. And now suppose we choose this function fx as x square. Okay. This obviously belongs to C01, right? Okay. Now, how can we detect, or how can we, kind of come out with the notion of an open ball whose center it as at F, let's say. Okay. So we try to, kind of find out the open ball whose center is at F and its radius is, let's say, half. Okay. How can we form this? Now see, basically what we need to find here is that a function which can bound a region whose center maps the function fx, and the region has its maximum distance from fx as half. Okay, the maximum distance between the boundaries of the region and this function fx is half. Okay, and this function fx, it acts the role of the center of this region. It passes to the center of the region. It symmetrically divides the region into two parts, you might say. Okay, so can we form the UF2 graphically like this? So suppose this is 0 and this is 1. So x square is something of this sort. Okay. Or let me, yeah, 1 second. Something of this sort, right? So if you move half upwards and half downwards, this is fx. Okay. This is say fx plus half, and this is say fx minus half. Okay. Let this be f1x and let this be f2x. Okay. Will this form this open ball? Obviously, because if you choose any function in this region, if you choose any function this region, see, if you choose any function from this region, let's say a function of this sort. Okay, the region, the distance between fx and this function, the maximum distance between fx and this function, and is half, right? Is half. And basically, if any function, in this region touches at least one of the boundary at a point, then you will get the closed ball, and these functions itself denote the sphere. Okay, these functions denote the sphere. Is it clear? Is it clear? Okay, simple, right? Achha. Now let us move on to the next concept, which is the concept of an interior point, and interior. Okay, so we will now be talking about the concept of interior point and interior of a set. Very important to understand the concept of open sets. Okay, so let xd be a metric space. Let xd be a metric space, and let us choose a set from a let's set from x. Let's take a set from x, and let us take an element from x. Okay, now by definition, a is said to be an interior point of a if there exists some positive real number such that the open ball centered at a and radius r, it is completely contained in a. Okay, it is completely contained in a. This is the definition of an interior point. Clear? And collection of all those interior points gives you the interior of a set. Okay, it is denoted by a naught. A naught is called the interior of a set. Which is basically the set of all those elements of x such that u x r is contained in a. The set of all the interior points. Is it clear? Let us take an example. Let us take this interval closed 0 open 1. Okay, and the metric is r with usual metric. Okay. So can you find the interior of a? See, every element you take from within this interval has at least one such positive real number such that the open ball is completely contained in a, right? Except 0. Because see, so this seems to be the interval, so this is 0. Okay, so every neighborhood, see, this open ball basically resembles a neighborhood, right? So every neighborhood of a is not completely contained in a. So a0 is the open interval 0. You can also see that any interval you take, the open version of it is only the interior point. Okay. Right here. In a similar way, we can check that the interior of natural numbers, the interior of rational numbers, as well as the interior of irrational numbers are all null. Because between, so if you talk about the natural numbers, Between 2 and 3 there are no elements. Also let's say 4. So if you take a neighborhood of 3, there exists no such element, which the open ball has no element except 3. So we cannot say it is completely contained in A, because let's say this is the set A. Clear? In case of rational numbers, what happens is that between any two rational number there obviously exists an irrational number. So any neighborhood you take of any number in Q, right, or any open ball you take centered at a rational number, its neighborhood or the open ball will always contain irrational number, but that is not contained in the set of rationals. Right? Same goes for irrational cases. Is it clear? Is it clear? Now, if you try to just verify the concept using the shape, so it is simply like this, right? So suppose this is the set A, and let's say A is an interior point. So A has at least one such element, such that the open ball centered at A and radius R is completely contained in A. That is the simple pictorial representation. Is it clear? Is it clear? Also there is one trivial case here. Also there is one trivial point here, that the interior of a set will always be contained in the set. Will always be contained in the set. And if A is contained in its interior, that is if A is equals to its interior, that is the whole of A resembles the interior of itself, then we say is an open set. Then A is an open set. Is it clear? Then A is an open set. Is it clear? Okay. Next we define a very corollary concept from here, which is called the exterior point. Okay. So let me define it directly. So a point A, we are considering the same metric xt. Okay. So a point A is said to be an exterior point of A if it is an interior point of x minus A. If it is an interior point of x minus A, or mathematically you can write it like if if there exists a positive real number such that the open ball centered at A and radius R intersection x minus A is completely contained in x minus A, right? Again, if you try to understand this pictorial representation, suppose this is A and A is a set of x, so suppose this is x, and if you take a point from here, let's say A. Okay, so this is the open ball centered at A and radius R. It is completely contained in x minus A, so it is an interior point of x minus A. Clear? Got it? This is the concept of an exterior point. Clear? Or you can write it like this, that the exterior of x minus A simply resembles the sorry write it in a more proper manner. The exterior of A simply resembles the interior of x minus A. Is it clear? And what is a boundary point? A boundary point is such an element such that every open ball you take centered at that particular point, its intersection with the set is non-empty, and its intersection with the set outside it is also non-empty. Okay, so boundary point. Okay, A is said to be a boundary point of A if and only if for all positive real numbers, open ball centered at A and radius R intersection A is non-empty, and open ball centered at A and radius R intersection x minus A is also non-empty. Pictorially, let's say this is A, this is x, you take a point from here. So if you form any ball, so its intersection with A is non-empty, its intersection with x minus A is also non-empty, so it forms the boundary point. For example, 0 in the interval, closed 0, open 1. right? 0 in the interval, closed 0, open. Let us check the last example from here. Let's say, suppose you take this, right? This is the same example. So we have already known that the interior is this 0.01. Okay, what will be the exterior of a, so every point outside this interval, right? So it is minus infinity to 0 union 1 to infinity, right? And what is the boundary point? What is the boundary point? So it is 0 and 1 is not a boundary of it, an existing boundary of it, but it will still resemble a boundary point. You can draw it and check it on your own. Okay, and from these three things which we have concluded from this given example, we can conclude one more thing. That is, for any metric space XD, X can be written as the union of its interior, the union of any interior of a set, exterior of that set, and the boundary point of that set. Okay, so let me give this as an exercise. You can try it on your own. Very, very simple, very trivial to understand. You just need to show that if you take any element from X, hint, if you take any element from X, either a below, so it is an element of some interior of some subset, or it belongs to the exterior of that subset, or it resembles the boundary of that subset. You can very trivially prove this. Okay, so the next lecture we will be talking about open sets, and so meet you guys in the next